I'm going to talk about elliptic curves, which are a good thing to know about in general, but I'm also going to talk about them in the context of this course because they lead to certain holomorphic modular forms that people consider a lot and that we're going to want to use for examples. And a reference for elliptic curves is this textbook from Silverman, the arithmetic of elliptic curves. This is sort of the gold standard as a reference for elliptic curves. Is a really, really good textbook. So without going into too much of the algebraic geometry, elliptic curves are projective varieties, and you can take a model for them of the following form when the characteristic of the field you're working with is not 2 or 3. When it is 2 or 3, you have to do something more complicated, but it's more or less the same thing. And one quantity that we're going to be interested in is the number of points on an elliptic curve mod p. So I'll write this way. This is the number of tuples xy both of them mod p, so maybe without the parentheses here, such that y squared equals x cubed plus ax plus b. So we're saying the number of points on this elliptic curve here, p is not going to be equal to 2 or 3. And we're also going to add 1 to this quantity because this elliptic curve is a projective variety, and as a projective variety, it has the point 0, 1, 0 on it, which is not captured by just counting the solutions mod p. And we're going to define this quantity a sub p to be, so if we have the number of points on an elliptic curve mod p, that's well approximated by the quantity p plus 1, and then the difference we're going to call ap with a sign as such. And it's a theorem of Hasse, I believe, that the absolute value of AP is, well, at most 2 square root P. There are some specific P's where something sort of weird is going to happen. So the discriminant of your elliptic curve, this is going to be a quantity that I'm going to define to be minus 16 times 4a cubed plus 27b squared. This is essentially the polynomial discriminant of this right-hand side. And when p divides your discriminant, you have what's called bad reduction. And otherwise, you're said to have good reduction. So bad reduction comes in 2 forms when p is not 2 or 3. You have you have multiplicative reduction, and you have additive reduction. So multiplicative reduction is when you reduce mod p, what you end up getting is a node, but not a cusp. So it's going to be hard to draw. Let's see. You get something that looks like this, and additive reduction is a cusp. So it looks like this. And more concretely, this is the case where, what is it? P has to divide A. Yeah. So this is when P divides A, and this is when P does not divide A. Again, this is all for P not equals 2 or 3. And in this case, it follows that AP is 0. And in this case, you have AP is 1 or AP is minus 1. The case AP is 1 is when you have split multiplicative reduction. And this is called non-split multiplicative reduction. And what these mean, split and non-split, is you look at the tangent line, and the slope of this tangent line either is or is not defined over your ground field FP. And so when it is, you have split multiplicative reduction, and when it is not, you have non-split multiplicative reduction. So these cases are important to know about because you also have this quantity NE called, so maybe I should write down here, this is called the discriminant. And then you have this other relevant quantity called a conductor. Of your elliptic curve, and it's defined to be the product over the primes that divide your discriminant, and the exponent is going to be 1 if you have multiplicative reduction, and it's going to be 2 if you have additive reduction. And, well, okay, this is for P not equal 2 or 3, and then if for 2 and 3, you have P to the, and then some mess. These exponents are bounded, but they can get up to, I think, 8 and 12 or something. I'm not sure. 2 and 3 are kind of annoying. Most people just assume that P is not 2 or 3 for all applications, and we're going to do the same. Okay, and there are L functions associated to elliptic curves, and these are defined as follows. So they're defined via Euler product. P divides the discriminant. And here you have a 1 minus APP to the minus S to the minus 1 when you have bad reduction. And then when you have good reduction, you get an extra term, which is P to the 1 minus 2S to the minus 1. And there's it's a long story for why exactly you get this. That's quite interesting and good to know about, but gonna not talk about right now because it's not super relevant for this course, at least in the immediate future. And this L function satisfies a functional equation. The functional equation is as follows: square root n over 2 pi. Here n is ne. This is the conductor of the elliptic curve. To the s, gamma of s, le of s, and then this is equal to some root number, which I'll talk about in a second. Here you have a 2 minus s, gamma of 2 minus s, le 2 minus s, and w is plus or minus 1 as called the root number. So some elliptic curves have w equals 1, some elliptic curves have w equals minus 1. Conjecturally, it's 50-50 among elliptic curves, but knowing which is which, it's tricky to figure out. And I will say that this normalization of the L function is called the arithmetic normalization. So what is the point of pointing this, of saying that this has a normalization and pointing it out? Well, this is an L function that goes between s and 2 minus s, right? So the critical strip has width 2, going from 0 to 2. And you'll note that that's different than, say, the Riemann zeta function, where the critical strip is going from 0 to 1. In this arithmetic normalization of an elliptic curve L function, the center of the critical strip is at s equals 1. The point s equals 1, when you're talking about, say, the Riemann zeta function, that's where it has a pole, that's the edge of the critical strip. That tells you stuff about like the prime number theorem, stuff like that. So the point s equals 1 has significance in both cases, but what the significance is actually quite different, right? Because here the point s equals 1, that's the center of the critical strip, and your L function, if your root number is minus 1, then you can see, in fact, that your L function must vanish at the point s equals 1. And that has some meaning. So the center of the critical strip has significance, and the right edge of the critical strip has significance. So when you say s equals 1, you should clarify whether you're using the arithmetic normalization, meaning that s equals 1 is the center of the critical strip, or this is in contrast with the analytic normalization. Which is just a simple linear change of variables that makes it so that the L function instead goes between s and 1 minus s. And in that case, s equals 1 would be the edge of the critical strip, and s equals 1/2 would be the center of the critical strip. Okay, so we have this functional equation for the L function, and another fact is that LE of S is entire meaning holomorphic on all of C, so it has no poles. I mean, it has an analytic continuation too. To a function that is entire. So in addition to Silverman's book, which is maybe the best reference for all this stuff, another reference for this is Ivaniach's textbook, Topics in Classical Automorphic Forms. And this is chapter 8 in all of this. It's an ugly 8. Okay. And that'll give you maybe a more to the point exposition of all these things, and all with a view of being useful for manipulating modular forms. So where do the modular forms come in for all of this? Well, there's this really crazy theorem. So if we take f of z to be just this function, some n from 1 to infinity, a n e n z. So again, remember that I'm defining e of whatever to be e to the 2 pi whatever. So we define this where a n is the it's going to be, let me do it this way, where AP is p plus 1 minus the number of, here's a better way to do this, where an is the coefficient, is the Dirichlet coefficient in the L function that we saw above, right? So that we can write this L function associated to an elliptic curve, which we defined in terms of this Euler product. We can write it as a Dirichlet series using the usual Euler product business. And we take that Dirichlet series and we stick it into a Q expansion. And then there is this really crazy theorem that was one of the biggest accomplishments for number theory in the 1900s. The function f of z, or the function f, as defined above, is a weight to cusp form of level equal to the conductor of the elliptic curve. And I mean, really, this is extremely remarkable. In fact, it is a new form, and in fact, it is a Hecke eigenform. Wow. All right. So this is why we care about these things, is because this is a great source of examples of holomorphic modular forms, right? People really care about elliptic curves, and so they care about the modular forms associated with them. And there are conjectures for higher degree analogs of this. An elliptic curve is a curve, right? As a projective variety, it's one-dimensional. If you have higher dimensional projective varieties, then you end up conjecturally getting modular forms through more or less the same story, but now these ANs, they're a little bit trickier to define, and in particular, they're algebraic integers with degree equal to the dimension of the variety that you're working with.